Go ahead and get started. Hello again, and thanks for joining us today. I'm Salah Farouqi, the lead R&D scientist at Petrolern, and I welcome you to the session number 19 of the P.A.S.S Talk series, where we are going to listen to a very interesting presentation by Dr. Joe Batir. I would like to thank all the speakers who accepted to give a talk in this series. We have 6 more exciting talks scheduled for the month of June, and we are now working on the schedule for the month of July. If in case you are interested to give a talk in this series, please send me an email or contact us at info@petrolearn.com. Our next seminar is June 16th by Carrie Loudon, titled An Overview of Machine Learning Technology for Seismic Interpretation with Case Studies. As you all know, we are still experiencing a difficult time because of the COVID-19 and the reopening, and that which has not yet actually helped the operation in the oil and gas to regain the steam. Therefore, we plan the future talk to be more centered on enhanced geothermal energy, subsurface CO2 storage and monitoring, which seems to be more attractive these days. We hope these talks open doors to new opportunity for people in oil and gas industry. Before introducing Joe, I would like to ask everyone to mute microphones in terms of cameras. If you have any question, please raise your hand at the end of the session and directly ask your question from the speaker. You may want also to write the question in the chat section for everyone. We will answer as many questions as possible at the end of the session. If for any technical and non-technical reason you could not stay with us until the end of the session, don't worry, we are recording the talk and it will be posted shortly now on our website. So Joe, so I'm now going to introduce our speaker today. Joseph Batir is a research geologist with the SMU Geothermal Lab. His research focus is surface and subsurface mapping for exploration and development, thermal, numerical modeling, and data mining to find underutilized energy resources. Joe produced the newest edition of the surface heat flow map of Alaska as part of his Ph.D., which included 4 field season and temperature logging and rock sample collection and lab analysis, including XRD, XRF, and thermal conductivity. His previous research included numerical code development to increase the efficiency and accuracy of heat flow calculation, funded by google.org RA Gradient Than C initiative. And most recently has produced a reservoir analysis in East Texas and new geothermal resource assessment of the Snake River Plain, Idaho, both in conjunction with NREL. So with that, I would like to turn it to Joe to start the presentation. Joe, please.
Salah, thank you for that introduction, and thanks everybody for joining us today. And today I'll be focusing on heat flow and the calculation of heat flow and temperature at depth, focused on bottom hole temperature data. So let's get to it. There we go. All right. So who am I and why am I the one talking? After I give a little bit more introduction, I'll dive into what is heat flow, why heat flow for thermal studies, and then how we measure heat flow, and then how it is used, talking specifically about the East Texas case study. And then I'll give you a brief snapshot of where you can find free data. So a little bit more about me. I got my PhD from SMU in geophysics, thermal studies of Alaska and British Columbia, examining thermotectonic processes, climate change, and crustal evolution. I spent 4 field seasons in Alaska collecting this data, and now I'm currently a researcher at SMU. I've worked all over the US and some internationally, mostly within Alaska, the Snake River Plain, California, and basins including the Illinois, Michigan, East Texas, Permian, and Anadarko basins. And then I've also worked in British Columbia, Iceland, Sao Tome and Principe, and the United Arab Emirates. My interests are the heat flow and thermal modeling applications for resource exploration, development, and production, and unconventional geothermal energy production, as well as isolated energy resource development. Before I go further, I do want to acknowledge and thank my multiple collaborators. All of these groups in some way have shaped everything that I am talking about, and at different times. So I just wanted to recognize all of them now. This includes the National Renewable Energy Lab, NREL, at Cornell University, Dr. Jefferson Tester and his research group. That includes George Stutes, Jared Smith, Calvin Welton, Aaron Camp, and Andrea Aguirre. And then the University of North Dakota, Dr. William Gosnold's research group, and also the University of Texas, both the BEG and currently with Team Geo. Okay, so what is heat flow and why do we care? So simply put, heat flow is the heat flowing from within the earth to the surface for a given unit area. The common units used today are milliwatts per meter squared, and this is a function of thermal conductivity and geothermal gradient. Most of what I look at is one-dimensional. So looking at the equation here on the right, we're talking about heat flow is equal to the thermal conductivity multiplied by the geothermal gradient. Specific assumptions that are worked into this 1D equation are that we are at steady state, so heat flow is not changing with time. This is one-dimensional in the vertical direction. This is quote-unquote constant in the upper kilometers, and we're at equilibrium with our surroundings. Now we know these are just assumptions, so there are certain corrections that can be made to help make these assumptions true. There are specifically things that often need to be corrected for are terrain effects, any type of drilling disturbance or visible not at equilibrium temperature measurements, climatic warming in the near surface, and fluid flow within temperature measurements. So why heat flow? Well, heat flow is quote unquote constant in the sedimentary section. So when we're looking at a hypothetical section here, looking at rock type, it is varying within the stratigraphic column, changing with depth. With each change in rock type, you have a change in thermal conductivity and a change in geothermal gradient. But the heat flow should be relatively constant with all of the assumptions that are incorporated throughout the entire sedimentary section. Now there is some level of measurement error, but that measurement error is roughly equal to the heat flow change. Within the sedimentary section, there will be small amounts of radioactivity, somewhere on the order of 1 microwatt per meter cubed, which equates to about 1 milliwatt per meter squared for a kilometer of section. So the measurement error is roughly 10%, which means if you're looking at something that has 80 milliwatts per meter squared, your measurement error is around 8 milliwatts per meter squared. So your measurement error is actually greater than the change in heat flow for any depth that you would be measuring and exploring in. The main point here is that the gradient changes with rock type and formation. So depending on where you are within the rock section, you could be measuring a very low gradient or a very high gradient. And if you try to extrapolate that gradient from surface to depth, you're going to end up misrepresenting or calculating the wrong temperature at your depth of interest. So by using heat flow, you can generate more accurate temperature estimates with depth. And that means you can get improved thermal models. You can have a better understanding of your subsurface conditions. And you can also use that heat flow to look at sections that are either above where you have your measurement, or you can go below. So you can upward and downward continue your thermal regime estimates. So from the heat flow, you can then calculate temperature at depth, and you can calculate it at any depth within the subsurface. There are some assumptions that go into this. Again, you're assuming a steady state temperature, which means the temperature is changing with depth, but not with time. There is the additional radioactivity from the basement and the radioactive elements within felsic rocks. This you assume is a one-layer exponential decay radioactivity model. And then we also assume homogeneous rock sections. So for every formation, each of those formations has a individual conductivity value that then discretely varies as you change from, say, a limestone to a sandstone. You have a one value for that limestone and then a different value for that sandstone. So they vary discretely with rock type and with depth. So here, this equation is basically looking at the change in temperature with time in respect to depth and time is equal to the heat flow. This is the heat flow here. You've got your thermal conductivity and then your gradient with respect to depth plus your radioactivity added in. Now, if we integrate that at steady state, which means there's no change with respect to time, so we have to integrate with respect to z, and we now have an equation to calculate temperature at depth, any depth of our choosing. This first section here, this first component, is the temperature within the sedimentary section. The second component is the temperature contribution from the mantle, so the deep temperature. And then this last component here is the temperature contribution with respect to radioactivity. So now we can look at any depth and calculate the temperature at that depth, provided that we have values for all of these inputs. And then all the inputs are here on the right. Feel free to grab a screen capture. This is also in many of our published papers that go into greater detail on how this is derived and how you look at specific scenarios. But that's really the benefit of going through this. We now have an equation, and for any individual well, you can have a different subsurface lithology scenario that requires different thermal conductivity model, to accurately calculate the temperature estimate. You could have something where it's one solid, say you're purely in basement, you have one thermal conductivity for the whole thing, or you have a variable sedimentary thickness, or you may have a variable sedimentary thickness and then two differing rock types, which just so happen to have the same thermal conductivity. All of these different scenarios require a different different set of inputs and a different amount of calculations where you're calculating z bottom minus z sed, but all of this has been incorporated into our automated code. And this is the bulk of this is the crux of the problem, where we've been working on this since really the work started in about 2009, and we've been incrementally increasing the complexity and improving the code bit by bit as we've gotten more information and more ideas and more ways to incorporate all these different values. So just taking a quick step back, what if, because it sounds like a lot of work, right? Doing that for every individual well, even if there is a code, still seems like a pretty labor-intensive process. So what if we just use geothermal gradient? So we're just looking at the gradient, ignoring thermal conductivity, not worrying about heat flow. Well, as conductivity changes, the geothermal gradient is going to change. So if we're just looking at this upper section here, this has a high conductivity, which means it has a lower gradient. If we look at the bottom section, we have a lower conductivity, which means we have a higher gradient. Now, if we have a measurement down here versus a measurement up here for geothermal gradient, we're going to calculate very different bottom hole temperatures. And if we're interested, say, at the temperatures at 2 kilometers here, we may end up with very different calculations. We just have something in the upper section, we're going to estimate temperature at this depth of 60 degrees C versus a temperature estimate of 100 degrees C. So in this very basic hypothetical example, we've got a difference of plus or minus 20 degrees C from the correct value or the equilibrium value. And 20 degrees C may not seem like that much, but that could be the difference of, say, being in the oil maturation window versus being in the wet gas window. Or it could be the difference of a direct use geothermal project versus a low enthalpy electricity production project. So it is important to have accurate estimates. And if we have geothermal gradient holes that are, say, 400 to 500 meters depth, it would be best to accurately predict down to 2 kilometers versus drilling another well and finding out after spending all of that extra money that we're overestimating or underestimating the correct temperature. Okay, so how do we measure heat flow? The main things we need are geothermal gradient and thermal conductivity, a thermal conductivity model. The geothermal gradient, the ideal scenario is that you would have an equilibrium temperature log this is something that is measured after the drilling disturbances have subsided. It is a series of temperature depth measurements, and this can later be used to calibrate or correct bottom hole temperature measurements and also be used directly to calculate heat flow. The other, and if you can tell by the example here, the larger data set is bottom hole temperatures. These are temperature measurements they're recorded shortly after drilling, often with some type of well log to make sure the well log is within safe operating temperatures. The well tool, the logging tool. It's usually a single temperature at a given depth. And it's often, because it's recorded shortly after drilling, the drilling disturbance is still there. So the measurement you're making is not at equilibrium with the surrounding rock. There are corrections that exist to try and estimate equilibrium temperatures. The first example, which we show here as black crosses, is the Harrison correction. This is a quadratic correction that is related to depth. So it's a quadratic equation that tries to estimate the equilibrium temperature based on the depth of the well. The other correction shown here are the red crosses, and that is the Forster correction. That is a linear correction with respect to depth. Another type of correction is corrections that are made associated with time since drilling, or how long the well has been sitting undisturbed. This is one example is the Horner correction, which is a logarithmic correction associated with time. And ideally, you would, if you can, you would measure an equilibrium temperature log. But if you can't, you would have a correction that's basin specific, which then requires an equilibrium temperature log in your study area. Once you have, from the bottom hole temperatures, you then use the surface temperature and you can calculate a geothermal gradient, which is then a geothermal gradient for that entire rock section. So it's a very large average, but it gives you that temperature information. Then you need a thermal conductivity model. Ideally, you would have the ability to calculate an integrated thermal resistance model. Here you would have thermal conductivity of the rock, either measurements that are within the well, measurements within the same formation in the same field, or measurements from the specific rock type, which is really more of just an estimate. This is going from the best case scenario of within well measurements down to the worst case scenario, which are individual rock type bulk average estimates. And then you need a stratigraphic model. Here, ideally, you would have lithology logs from a well. Then you would have if you don't have a lithology log, you would have a local cross section, say within the field, or a general basin stratigraphic column. And then worst case scenario, you would use the correlation of stratigraphic units of North America. There's a large project that was done through the AAPG that made generalized stratigraphy throughout all of North America. If you don't have the ability to calculate any of those, then you would assume an average thermal conductivity for that upper section. At this point, with that, you're really just calculating you're just making a constant shift for your geothermal gradient, and you're really just changing the numbers. But if you have heat flow measurements already, that at least gives you an easy one-to-one correlation. So then I just want to show over here on the right, this is a picture of a divided bar apparatus. There are multiple different ways to measure thermal conductivity. This is how we measure thermal conductivity in the SMU Geothermal Lab. If you have questions about thermal conductivity, specifically in measurements and those kind of things, we can talk about that at the end, or you can always shoot me an email and we can talk about it offline. So once you have geothermal gradient and thermal conductivity, then you actually calculate heat flow with that by multiplying them together. So here, where you have, ideally you would have the temperature depth log, and then you can calculate individual intervals for geothermal gradient and thermal conductivity. You can see here, there's a shift from your gradient about here, your thermal conductivity slowly dropping into a more constant gradient and conductivity. So you can calculate your gradient and conductivity and a heat flow for every individual interval throughout this well log. And then your individual interval heat flows that are calculated can be averaged to get an average heat flow for that site. So here you've got your individual heat flows shown by the black line. And then an average heat flow would be roughly this red line. And then the uncertainty or the natural variability of the heat flow you've calculated is then that standard deviation within those different intervals. So this is the ideal scenario. What we're going to be focusing on for the rest of this talk is really looking at individual wells where you may have only one temperature measurement or or a few temperature measurements for individual wells. So here we're looking at a Bullard plot. This is a single well where we have 3 temperature measurements, 2 at casing points where well logs were run, and then 1 at the total depth. What a Bullard plot is a temperature versus the sum of the thermal resistance, or 1 over the thermal conductivity. So we've got thermal resistance and temperature. And if we plot a best fit line, when we plot these, the slope here ends up being the heat flow in watts per meter squared. And now here's the equation for the Bullard plot, where you've got resistance is equal to the integral of 1 over the conductivity with respect to depth. Your heat flow is your conductivity times your gradient. So then through combining these two, we can eventually get to the change in temperature with the change in resistivity is equal to your heat flow. So in this way, you can calculate a fairly accurate heat flow for individual wells where you have only a few data points. And this is more or less going to be more accurate than if you were to just calculate a gradient for these 2 individual points and then these 2 individual points, and then just average those. Here you are incorporating the variability of the conductivity throughout the entire section. The other option, say you only have one measurement at the bottom of the well, but you have 20 wells. So here we're looking at a single oil field that has 20 wells in it, each of them with a BHT. So we could do this, we could calculate a heat flow in 2 different ways. The first option is to calculate 20 individual values and use it spatially and look at this from a map perspective. That's something you could do for, say, infill drilling or well placement if you're to the point of development and trying to find new spots for wells. Or if you're still early in the exploration or have new ideas and you need to modify your work, you could calculate a single regional average value and use that for something like basin modeling. Ideally, you would be very close together with those wells. You can see here that we have wells that are not on this trend line, and those may be a little bit outside of the field, or their temperature may not be getting corrected correctly, or there may be some type of fluid flow occurring. So these are outliers that would then need more assessment. There's a higher error associated with these single point values, whether you're doing a regional average by combining a bunch of wells, or whether you're just calculating individual data points and then looking at it from a histogram or spatial view. But the real power here is that this is what we have automated. So we have made a code that calculates, it determines the total thermal resistance to each of these data points, and then calculates a heat flow for every one of these. And at that point, we have it and we can look at it spatially, and we can start making those data-driven decisions because we have the heat flow available, and we can start making other iterative products such as temperatures at depth or heat density or really whatever you may be interested in from that thermal perspective. So how have we been using this? Let's jump into East Texas. So we're looking at East Texas here, the Sabine Uplift region. We're going to zoom in here, right in here. This was a project with NREL and with the Eastman Chemical Company. They have roughly 6,000 acres of wholly owned property. They have both surface and subsurface mineral rights, and they have a 235 megawatt natural gas turbine on site that they use for their specific purposes and also combined heat and power. And their main goal with the focus of our project was to produce geothermal heat driven absorption chilling. And in doing that, they were going to use that cold water for inlet cooling for a natural gas turbine to improve the efficiency of that turbine. In this area, one specific scenario that I haven't touched on yet is areas with large amounts of salt tectonics or just in general salt basins. So here we're looking at East Texas. There are lots of different salt tectonics and salt plumes. In our specific study area here, there are a few small salt pillows. Salt has a very high thermal conductivity, so it actually is almost like a highway for heat. That's the easiest way to explain it. And it'll create, if it's a large enough structure, it will create a thermal anomaly where you've got a higher heat flow above it, because it's condensing that heat and making it travel quicker. So that was a concern of ours that we were looking at and examining, just to make sure that that's not another part of those geologic specific scenarios that need correcting for. Here I'll talk about it a little bit later, but that's also another thing that you have to keep in mind. And I also wanted to just do a quick touch again on the field scale versus the well scale. So if we were calculating heat flows for individual oil fields in this East Texas area, we would have about 14 covering a 4-county area. This is roughly 50 miles or 60-ish kilometers across. So we'd have 14 wells within that area. When we're looking at individual wells, we've got thousands of individual wells right here within this 20-kilometer zone. So you can see the circle, the area of interest, and how many data points we can have. The real key is, are we able to collect all of that data and calculate heat flows for all of those? Because there are thousands of wells, that seems like a fairly labor intensive process, but with our automated code, it is easier. So looking at the final data before this research, there were 121 Ph.D. heat flows. These are these pink data points. Those were in the SMU heat flow database. As part of this work, we went in to the Texas Railroad Commission, looked at the wells within the 20-kilometer radius. There were somewhere around 2,000. We ended up collecting 1,400 well logs and pulling off the temperature and depth from those, so from the BHTs, so that way we could calculate a gradient and eventually a heat flow. We didn't have any thermal conductivity measurements, so we looked at the USGS report from Pittman and Rowan 2012 from the Gulf Coast to get thermal conductivity estimates. And then we also looked at additional studies in East Texas to modify and refine the stratigraphic column. One thing I want to point out here, there are about 2,000 wells within this region, but we only looked at 1,400. Right now, what we have to do is we go in, we look at the well log header of an individual well, and we manually record the depth and the temperature. We haven't found a way to automate that process, and that's really kind of the bottleneck of this whole thing. And I'll touch on that more later, but that's why we only have 1,400 versus the available 2,000 data points, because we basically just ran out of time, allotted time for new data input. Here's the stratigraphy that we were working on. The temperature cutoff that Eastman Chemical gave us was about 100 degrees Celsius. From that, we knew that we were looking at primarily the Pettit, Travis Peak, and Cotton Valley stratigraphies within the entire stratigraphic column. These are shallow, shore face to shallow marine stratigraphies. The main reason I put this in here is to point out that our cutoff was 100 degrees Celsius. So we knew, given the thermal regime, this is the area where we're looking at. But if you have lower temperature uses, there are potential reservoirs higher up, such as the Austin Chalk, Eagleford, and Woodbine. Or if you need higher temperature, you could even go deeper to the Haynesville, Smackover, or Norphlet. And we can do that now because we have heat flow and we have the ability to calculate temperatures both up higher in the section and also go lower where we may not have direct temperature measurements. So getting into the results, the first result was the updated higher resolution heat flow study for the region. Now, I don't have them plotted, but if you remember, the salt pillows were somewhere around here and generally in this area around here. What we saw with those salt pillows was that there wasn't really much of a change in terms of geothermal gradient or heat flow focused on those. And our interpretation of that is that these were probably fairly thin sections. They weren't the typical salt pillows that you think of in the Gulf of Mexico that are creating hundreds of feet of relief that physically move the sediments. Here, we didn't see any change in these formation tops that we were looking at, and we didn't see any change in geothermal gradient. So we interpreted that as meaning we were outside of their depth of influence. But it is something that we looked at, and if we were to project the temperatures deeper, that's something that we would have to consider and think about where those start to impact the temperatures with deeper depths. So now that we have the heat flow, we can further estimate the temperature at depth, the volumetric heat density, because we have the different thicknesses of the formations and the different reservoir properties. This is similar to just reservoir volumetrics. And then we can start making those data-driven decisions, such as looking at different economic analyses and scenarios and looking at future well placement. So the second result that we got from this is temperature depth estimates for each individual point. We could go from there and calculate total estimates per formation. And we did this as a first step to get median values and median numbers. We could see here that the petit is actually, the median temperature is right around that 100 degrees C cutoff. This is the median, which means we're going to have higher and lower. But the petit is probably too low of a temperature for our studies. And it also had a fairly low geothermal gradient. So what we could say is any further analysis, we don't have to look at the petit. We can just look at the Travis Peak and the Cotton Valley. So we've now saved ourselves we've removed a third of the work from the rest of the analysis, because we know the temperatures aren't going to be, more than likely won't be sufficient. But now we can start looking at maps for nearly any criteria, specific formations, temperature cutoffs, or depth cutoffs. So here we're looking at the Travis Peak formation top temperature. And I've blown up the temperature categories for you so you can see it a little bit better. At this point, we've got this in a spatial sense, so we can start looking at areas to remove that are outside either our minimum temperature or our heat density, etc. We could also remove areas that analysis if we don't have a high enough data density, or if we don't have some other sufficient criteria, if the data are too low a quality. And we can start using these maps to look at different reservoirs based on output values and start playing that economic scenario game. Here, specifically for East Texas, we can now say, okay, Eastman Chemical, everything on this eastern side of your property is not going to be high enough temperature, so we can cut that out. We don't have to look at that. We can focus in on this western side of the property. And then with going to that next scenario running, we can look at the heat density, looking here at specifically the Travis Peak versus the Cotton Valley and the heat density within those formations. We have a lower heat density overall in the Travis Peak versus a higher heat density in the Cotton Valley. And the highest heat density, this little sliver right here, kind of right in the middle of the property, is also, it ends up being consistently high in both the Travis Peak and the Cotton Valley. So if I were to make a recommendation, if we were going one step further and starting to look at well placement and well economics, we would focus in on this specific area, and then we would have to start running those numbers of the Travis Peak depth and how far we're going to have to drill, how much that well is going to cost versus drilling to the Cotton Valley. What is the heat density? How much thermal energy will we be able to pull given those numbers? And overall, which is the best well that we can do? And this is also a little bit more stacking the deck, because now we have a plan B. If the Travis Peak, say, is plan A and doesn't work out, we can always drill deeper to the Cotton Valley or vice versa. And we can start playing that risk analysis game and economic evaluations based on these results that we now have. So looking at what we've got here, we now have a point-by-point heat flow calculation model that increases the thermal regime modeling resolution. We can look at the thermal regime with depth and with given scenarios and given temperature or heat density cutoffs. Using this developed code, this is a quicker, more cost-effective way to calculate heat flow and temperature at depth. We can do this provided that we have all of the necessary inputs, and we can also look at how our uncertainty changes if we don't have necessary inputs and are just putting in estimates, because it's automated and we can run those different scenarios. As I said, this gives us the ability to examine the subsurface thermal regime from multiple angles, including depth, temperature, heat density, really whatever your specific purpose is. We can now look at it, and we don't have to worry about how long the modeling takes, because we have it here ready to go. As I said, the limiting factor is the time and cost intensive process of collecting that initial data. Right now, we have to manually record data from the well log headers. This could be improved through some type of text recognition abilities, and something that is beyond what it seems like Adobe OCR can do. And it may exist, but we've never been able to find something that works. So jumping into big picture ideas and trying to summarize the major benefits here that I've talked about. The data density versus depth. Really what we're looking at is heat flow versus geothermal gradient. If we're looking at the Pettit, this is the top of the depth regime that we were looking at, versus the Bossier is the bottom. If we're looking at just the top, we've got more data, but say we want to get to the bottom, say we want something at 10,000 feet, we're going to have to, if we have heat flow, we can then calculate and downward continue to those depths. Whereas with geothermal gradient, we may end up miscalculating the geothermal gradient, or miscalculating the temperature at depth, which will then give us a misrepresented temperature and may be a poor model. And then the current limiting factor that I said is the individual well log analysis. So this is a well log from Idaho. We have to go in, collect well logs, and get these depths and then the temperatures. This is tedious, it's very time intensive, and as you add up the amount of time it takes, it quickly gets cost prohibitive. So we haven't found a way to automate this yet, but that is really the choke point and what still needs to be improved within our whole process. But here's the main point, is that the black dots are BHTs versus these blue dots are equilibrium data. The black dots are more widespread, they're more spatially relevant because they cover a much larger expanse, and there's more being produced all the time. This is the data from the 2011 SMU heat flow map. So how many wells have been drilled since 2011 that are new data that aren't even incorporated into this? That could be, as long as we can collect that data in a cost-effective way and then input it onto these maps. So real quick, here is, feel free to grab a screen grab or take a picture with your phone. These are just some specific sites that I have used and where I think you can find a lot of good data. Geothermaldata.org and geothermal.smu.edu are more national databases, whereas the GDR, OpenEI, and the Great Basin Center for Geothermal Energy, those are more project specific and location specific. The International Heat Flow Commission they house the global heat flow database and a borehole temperature database for climate change modeling. And then geothermal.org is the Geothermal Resources Council. They have an extensive library that's open access of lots of previous geothermal research, and that is that they have an annual meeting that has international attendance on all aspects of the geothermal industry. So I encourage you to check out these websites, see what data is available, see what you're interested in. And if you have any further questions that we can't cover during this question time, feel free to email me, connect with me on LinkedIn, and shoot me a message. I'll help with whatever questions or whatever ideas you have in mind. Open to all ideas. With that, I do want to thank Petrolern for their time and for letting me present on here. And I hope you've all learned something today. And with that, I'll open the floor for questions.
Thank you for the presentation, Joe. It was very informative. Now we can go ahead and take some questions from the participants. First, let's see if anyone wants to ask you any question directly. If not, I got a couple of questions in the chat section that I can read them through for you to answer. Anyone wants to ask question directly? If you want, please raise your hand so I can see it. Alan, do you want to ask your question directly?
Can you hear me?
Yes.
Yeah, I was going to ask early in the presentation about salt, but you covered that. Does thermal conductivity have a stress dependence?
In some respects, yes. It has a temperature and a pressure dependence, and it's more impacted by temperature. In terms of pressure, it's a fairly minor change associated with pressure, but what's probably more important is the change that is going to occur if you start metamorphosing the rock, because for shales, they have an anisotropic thermal conductivity, which means they have a higher thermal conductivity in the XY plane as opposed to versus the Z plane. So as you're changing the mineralogy makeup and the stacking of the rock, that'll change the thermal conductivity and change how heat will flow through individual
Thanks.
Thank you. So I have a question from Usman asking, when you do the calculation, do you take into consideration other modes like convection and radiation, or it's just conduction?
So it is, with that equation, it is just conduction. We add in that radioactivity component, which is also a conductive heat transfer. The convection, there are specific scenarios and specific areas where we do look at convection, but as a whole, and this is one of the major assumptions that could be improved upon. As a whole, we assume that within the crust, the heat transfer is dominated by conduction. So we know that that's not the case once you start getting down to the mantle and potentially past the brittle ductile transition zone. You might start having a larger convective component. But for the section that we're looking at in the crust, we think that assuming a conductive heat flow is within measurement error, so to speak.
Fair enough. The next question is from Pierre Francis asking, do you see any advantages in using distributed temperature sensing like fiber optic for those specific applications that you just discussed?
There are a lot of benefits to the fiber optics. It is, with the fiber optics, you're collecting real-time data and you can see the temperature change with time, because we know that that's, if you are doing any type of production or injection or any if you are impacting the thermal regime in any way, then having that data is important. That would be similar to having, for our purposes in calculating heat flow, that would be similar to having a equilibrium temperature log. So it's important if you are monitoring and developing and maintaining an active field, and it's more important there, I would argue, and I would say should be necessary for many wells. But I think for early exploration, such as what we're focused on, I think it would almost be more of it would be an extra cost that isn't necessarily warranted.
Okay, and one follow-up question on that one says, what type of logs did you use to drive the rock thermal properties?
Most of the rock thermal properties, so the thermal conductivity will be measured in our lab. We'll collect rock samples and measure them on that divided bar. You can use the velocity logs to estimate thermal conductivity, and you can use a spectral gamma ray log to estimate radioactivity. And then any conventional well log that gives you estimates of the rock type, you can then use to build a thermal conductivity model based on estimated thermal conductivity values.
Very interesting. I think we don't have any more questions. Let's wait for another minute to see if any question will come up. If not, then we will call it the day. So, any more questions? So I think we don't have any more questions. Thank you so much, Joe, again, for this nice presentation. Please follow us on LinkedIn to receive updates about the P.A.S.S Talks. With that, let's go and enjoy our Friday. Bye all.
Thanks, everyone.